Let's take a look at our first material here. We got our inverse functions. Okay. Now remember our function said for every x there's only one y. Now we have something called a OnetoOne function. It says for every x there is only one y, and for every y there's only one x. So it goes both ways. We got an easier definition of a OnetoOne function. It says if you have any of the following, it is not a one-to-one function. If you have x to an even power, if you have y to an even power, then it's not a one-to-one function. If you got the absolute value of x, if you got the absolute value of y, if you got the plus or minus symbol, unless there is a condition put on x. What I mean by that is you have an example where you have like y is equal to x squared. Now that right there, the fact it's got an even power means it's not a one-to-one function. But if we put a condition on this, we say x where x is greater than 0. By putting that condition on there, we're ensuring that it's a one-to-one function. Now, the first topic here, identify one-to-one functions. Using this, if we had an example, and the question was asking us to identify the one-to-one functions. These are yes or no. This one here, y is equal to x squared plus 3, the fact it has an even power means no, it's not a one-to-one function. Now this one here, we said we can't have x to an even power, y to even power, absolute value of anything, or plus or minus symbol. These are odd powers. We can have those. So this one, the answer would be yes, it is a one-to-one function. Now what that plus or minus looks like is you'll have y is equal to plus or minus square root of x. You can have a plus, you can have a minus, but you can't have this plus or minus symbol. If you have that, then the answer is no, it's not a one-to-one function. Now we also have a graphical way to determine if something's one-to-one. We had the vertical line test that told us about whether something's a function or not. And we got a horizontal line test that says if any horizontal line can intersect the graph at 2 or more places, then it is not one-to-one. It might still be a function, but it's not one-to-one. An example of that. This is the graph of y is equal to x squared. And the question becomes, can we drop a vertical line somewhere that intersects at 2 or more places? Well, if I put one here, it'll intersect at 2 or more places. So the answer to this one is no, it's not a one-to-one function. Now on the other hand, if we looked at the graph of y is equal to x to the third, look something similar to this. I asked the same question, can I drop a horizontal line somewhere that intersects 2 or more places? I drop one here, it intersects one place, drop one here, one place, drop one here, one place. There's no place I can drop a horizontal line that intersects at 2 or more places. which means that, yes, this is a one-to-one function. Now, that was our horizontal line test. And those are the two ways we have to tell if something's a one-to-one function. Now, next part starts talking about what an inverse is. So let's go over that. Let's take a look at what is an inverse. This will be graphically. It would actually help if I could draw this without having my lines crooked, but okay, so let's say this is our function, and we want to find our inverse. This point right here is 1, 4. This point right here is negative 1, 1. And this point right here is negative 3, 0. Okay, now that point's 1, 4, so our inverse will be 4, 1. It'll be 4, 1. This is negative 1, 1, so our inverse will be 1, negative 1. This point here is negative 3, 0, so our inverse will be 0, negative 3. So if I draw those, lines through those, that is, more or less looks like this. This is represented by what looks like f to the negative 1 power. That's not f to the negative 1 power. That means the inverse of f. And while I don't draw these very well, if I graph the line of y is equal to x, right through the middle like that, inverses are symmetric to this line, which means if I would take this graph here and flip it, reflect it across this line, it should land exactly on this part of the graph. That's what it means to be an inverse graphically. Now we also have an algebraic definition of what it means. So our inverse definition, this is our algebraic. F and G are inverses, or our functions, and are inverses if the following is true. If the composition of f and g is equal to x, and the composition of g and f is equal to x. This is what it means to be inverses algebraically. For example, let me clear this off. If I got f of x is equal to 2x minus 1, and g of x is going to be equal to 1/2 x minus plus 1/2. And if the question is whether these are inverses of each other, Well, if I find the composition, I'll do this way first, of f and g. This little O-looking thing, remember, is composition. That means f of g, which means we're going to take our f of x, which is 2x minus 1, and everywhere I have a variable, I'll put parentheses. Now, whatever's inside the parentheses right here is automatically we'll put in down here, so we'll put g in there. But g is equal to 1/2 x plus 1/2. And now if I simplify this, 1/2, or 2 times 1/2 gives us 2/2, or 1x. 2 times 1/2 is 1. Then I bring down to minus 1. And 1 minus 1 gives us just a simple x, which is what we're wanting. But we also have to find the composition going the other way. Composition of g and f, which is g of f. So I'm going to take my g of x, which is 1/2 x plus 1/2, and where my x was, I'll put in parentheses. Whatever's inside the parentheses here will automatically go in here, so I'll put f in there. But f is equal to 2x minus 1. So then 1/2 times 2x gives us x. 1/2 times negative 1 gives us negative 1/2. And then I'll bring down the positive 1/2. And negative 1/2 plus 1/2 cancels and simply gives us an x. Since both of these come out to equaling x, then yes, these are inverses of each other. And that's what this definition says. Now let's take a look at how to find the inverse. So finding the inverse of a function. Okay, step 1. Replace f of x with y. Step 2. Interchange x and y. Step 3. Solve for y. Step 4. Replace y with our inverse notation. And then step 5, if necessary, use the graph to help figure out how to make the inverse 1-to-1. I'll grab a drink here. Let me clear this off. Okay, we got f of x is equal to, let's say, 1/3 x minus 5. And we want to find the inverse. First off, this must be 1-to-1. So that's why we covered the 1-to-1 part first. If it's not 1-to-1, then it doesn't have an inverse, and we don't even want to solve it. Well, this doesn't have any of the bad items. It doesn't have the x to the even power, y to the even power, absolute value of x, absolute value of y, or plus or minus. So it is 1-to-1. Step 1. Replace f of x with y. So we're going to have y is equal to 1/3 x minus 5. Step 2 is interchange x and y. Swap them. So where the y is, you put an x, and where the x is, you put a y. Step 3, solve for y. Get rid of parentheses. We don't have any. Get rid of fractions. We do have that. We'll multiply everything by the LCM of all their denominators. So multiply everything by 3. So I'll take 3 times x, and I'll take 3 times 1/3 y minus 3 times 5. So we got 3x. Here the 3's cancel. I get 1y or y. minus 3 times 5 is 15. Takes 15 over, and because of positive 15. And then step 4, replace y with our inverse notation. So we'll have the inverse of f is equal to 3x plus 15. I apologize for some of the noise in the background. Our air conditioning broke yesterday. And so now I got the windows open just so I don't die from the house being too hot. And so you're hearing a lot more of the outside traffic and so forth. Okay, that was the third item. Find the inverse function. Now, section 4.2, exponential functions. And the first topic it talks about is graphing exponential functions. So let me clear this off. Example, if I have f of x is equal 3 to the x. Now what makes this an exponential function, of course it's a function, but what makes it an exponential function is we got a variable in the exponent. Now to graph this, we'll go to our y equals, press clear, then we'll do 3 caret x. You don't need that 0 in y2. That's left over from previous problems, so we go clear it out. And then I push graph. Now these never just stop. So when I'm sketching this graph, it actually looks like this right here. Keeps going forever. We're just skimming the x-axis, never touching it, never crossing, just getting closer and closer to it. And that would be our graph. Now let's consider if I have something like this. This specifically is where we have more than a single number or a single variable in our exponent. The trick here is to put parentheses around the exponent. So we'll plug it in. We want to go with 2 to the x plus 3. So pressing y equals clear. Do 2 caret beginning parentheses, then x plus 3, and then closing parentheses, and then graph. And our graph looks like this. Now one more graph, and that's where we have e to a power. Well, e is just a number. It's kind of like pi. And how you get e on your calculator is you'll do second and then natural log. Other than that, you probably will type as you see it. So press my y equals, press my clear, do second ln, it puts e caret beginning parentheses. Then I'll do x minus 1. And you can put a closing parentheses on the very end if you want, but you don't have to have it. And press graph. And that would be our graph. You kind of notice on these, they all look alike. That's because that's the nature of exponential growth. They all follow the same form. Grow slow, and then flies out of sight. Grow slow, flies out of sight. Grow slow, flies out of sight. Whether we're talking about retirement, whether we're talking about little viruses, bacteria in your body, whether we're talking about mice overpopulating. That's the way that population grows. Whether it's population of mice, bacteria, or money. Okay. Let's see. Evaluate the login. Okay, we talked about that. Use to compute compound interest, exponential. Okay. There's two formulas for compound interest you may run across. And one of them looks like this. A is equal to P e to the RT power. And the other one is A is equal to P times 1 plus R over N to the nt power. Now P is our principal. A is our ending amount. R is our rate. And rate's in decimal form. T is our time, and that's in years. And N is the number of times compounded per year. The number of times compounded per year. Now this first formula you use if it says continuous. The second one you use if it does not say continuous. For example, if they told you the principal was $1,000 and they tell you the rate is 2% and we're going to leave it in the bank for 5 years and it's compounded continuously. Compound is a fancy business term, means calculated, but even more than that, it means calculate your interest and then put it back into the account. So it compounds, it builds. Okay, so we'll plug in those values. We'll put 1,000 in for the P. E, R was 0.02, and then times T, so we'll do a little times symbol here, times 5. Okay, so to put that in, exit out of graph mode, we'll do second mode. And then I got 1,000. E, which remember was second ln, and then 0.02 times 5. When you're typing that in, do not put any extra parentheses in. Extra parentheses will mess you up on this. You want to enter it exactly as I'm demonstrating there. So A is going to equal to 1105.17. That's how much would be in the account after 5 years at 2% interest if we put $1,000 in the bank account. On the other hand, if we're given something where P is equal to 2,000, R is equal to 3%, T is 7 years, and N is equal to 4, compounded quarterly. Usually N isn't given directly. They'll just say it's compounded monthly, N is 12, compounded daily, N is 365, and so forth. So if you're given that, then you can plug that in. So you got A is equal to 2,000, 1 plus R, which is 0.03, divide by N, which is 4, raise the NT power, which would be 4 times 0.03. So I got 2,000, 1 plus 0.03 divided by 4, and then 4 times 0.03 gives you 0.12. And that's where we're going to plug into our calculator. So we got 2,000, beginning parentheses, 1 plus 0.03 divided by 4, closing parentheses, caret 0.12. And then press enter. And that tells us that A is 2001.79. And that'll be our answer. Okay, let me clear that off. And It's actually everything out of 4.2, so let's go down to 4.3. We'll grab a drink here. It says to convert between log and exponential forms. So let's talk about those forms. We have our log form, is where we have log base b of q is equal to p. And then we got our exponential form, which is b to the p is equal to q. Now probably all these have names, but really the only one that has an important name is the b. That's referred to as our base. Now if I look at some examples here, say I got log base 2 of 7 is equal to x. And the question was to write that into exponential form. Well, it's in log form. Now what the b represents is it's a number that's smaller that's set down that follows your log. So this 2 here will be our b. And then whatever follows that is our q. So the 7 is our q. And then the other side of the equals is our p. Now our exponential form is b to the p is equal to q. So we just plug in what we identified. We said b was 2, p is x, and q was 7. So our answer would be 2 to the x is equal to 7. Now if I had this right here, 3 to the third is equal to x. And the question was to put it back into log form. Well, this is already written in exponential form. And we said with the exponential form, our power is our p. So this is our p. Then what's the left of it is our b. And then the other side of the equals is our q. Now our log form is log base b of q is equal to p. So we plug in what we identified. So b was 3, q was x, and p was 3. So that would be our answer. Now we have some special bases. If you got just simply log of something, like log x. There is no base. There's no number that follows it. We just have log. Then your base by default is 10. Now this is the common log. On the other hand, if we have natural log of something, ln, then your base is e. That's your 2.7, a bunch of decimal places. That's our natural log. Now we can use these same processes to rewrite these. For example, if I have natural log of x plus 3 is equal to 7. And the instructions were to write it in exponential form. Well, we have to identify our b, p, and q. B is whatever number's here, and since this says ln, that tells us b is e. And then what follows that is your q, and then the other side of the equals is your p. So our exponential form is b to the p is equal to q. So b was e, p was 7, and q is x plus 3. And that'd be our answer. Okay, let me clear those off. And that was converting between log and exponential forms. Now evaluating log expressions. This is best shown by example. After I show a couple examples, I'll write down the formula. Fairly simple idea. Sometimes it's not so simple to get in the right form. But we want to evaluate this without using a calculator. Now notice our base is 2. What we try to do is we try to rewrite whatever number's here as 2 to a power. And 8 would be 2 to the third. Now if these numbers match, then the log and those two numbers are going to cancel. The 3 will drop out of the exponent, and that's our answer. So look at another example. Now notice here our base is 3. And we're going to try to rewrite this as 3 to the power, and the square root of 3 is 3 to the 1/2 power. Now since the 3's match, log and the 3 is going to cancel, and 1/2 is our answer. Now this particular log property says we got log base b of b to the p. That's going to equal to p. Now we have another one. If you have 2 to the power of log base 2 of x, notice how the 2's match here. If those numbers match, then those numbers in the log cancel, and this, whatever follows the log here, drops out of the exponent, and that's our answer. So that's equal to x. Now, next topic we want to talk about is the I guess we just did that, graphing them. So let's take a look at graphing them. Let's say I'm going to graph y is equal to log of x plus 3. I want to graph y is equal to natural log of x minus 5. And I want to graph y is equal to log base 2 of x plus 1. Now this first one, y is equal to log of x plus 3. Then go to my calculator, do my y equals, clear. And I got log, so push my log button. This is base 10 of x plus 3. And then we'll press graph. Now the calculator always will show these wrong. They never just stop. See how this just looks like it stops? It keeps going on forever. So that's what it should look like. Now natural log of x minus 5. If I go to y equals, clear, and then natural log of x minus 5, and then graph. Now again, these never just stop. This keeps going forever. So it'll look like that, more or less. Now we have a log button, that's base 10. We have an ln button, that's base e. This is base 2. We don't have a base 2 button. What we have to do is we have to use something called the change of base. So this becomes log of x plus 1 over log of 2. Now how that works is whatever your base is, right here, that always goes down to the denominator. Now whatever follows your log is always what goes up on top. Now I might look at this and say that's more complex, yes, but now we can plug in our calculator because we have a log button. So go to y equals, clear, now do my log x plus 1, closing parentheses, divided by beginning parentheses, log 2. And then closing parentheses. Now if I graph this, it's almost what our graph looks like. More or less, that's what your graph looks like for that particular one. So anytime you have a base other than 10 or e, the log and the ln, if you have any number there, then you have to use change of base. I'm going to clear this off. Okay. These okay, we already talked about change of base there, so I won't show that again. These three here refer to the product, quotient, and power properties of logs, and talk about expanding and writing it as a single log. So let's talk about that. Got properties of logs. Our first property says log of something plus log of something is equal to log of the two items multiplied together. If we have log of something minus log of something, subtraction becomes division. And if we got a p log m, that's where we have a number in front of a log, or it could even be a variable. But we can rewrite that as our power. Now these are our three main properties of logs that we'll use quite a bit. So let's take a look at some examples. We got log of x squared y to the third over z to the fifth. And we want to write these as separate logs. Our goal is to get the variables by themselves with a log in front of them if we can. We always have to ask ourselves what's the main thing happening. Like here we got second power, third power, fifth power, we got multiplication, we got division. When I say the main thing, I'm talking about what would use everything. And that'd be division. Top part divided by the bottom part. That would use everything. Well, division from property 2 becomes subtraction. So this can become log x squared y to the third minus log z to the fifth. Now looking at our first set of parentheses here, we got multiplication. And multiplication from property 1 becomes addition. So this will be log x squared plus log y to the third minus log z to the fifth. Now remember, our goal is to get the variable by itself with the log in front of it. So we can't have these powers. So from our third property, it says if you have power, you can put it in front of the log. So this becomes 2 log x plus 3 log y minus 5 log z. And that's our answer. Now in some cases, you'll start out with separate logs and you want to merge them into one. So in this example, we have 3 log x minus 1/5 log y minus log z. In order to use properties 1 and 2, you cannot have any numbers in front of your logs. So keep that in mind. So right away I notice that these first two have numbers in front of the logs. So let's get rid of those. And we do that via the third property. If you have a number in front of your log, you can put as your power. So this becomes log x to the third minus log y to the 1/5 minus log z. Now on these, you pretty well follow your order of operations. So we'll handle the first two here. Log of something minus log of something. Well, that's our second property. Subtraction becomes division. So it's going to become log x to the third over y to the 1/5 minus log z. And again, we have log of something minus log of something. So subtraction becomes division. Specifically, where I'll put that z at is I'll just put it right next to the y to the 1/5. And that would be our answer. Okay, let me clear that off. And we're ready for section 4.5. solve exponential equations. Grab a drink here. This is an example of an exponential equation. You got an equation and you got a variable in the exponent. That's exponential equation. Now we have one technique of solving these. That's called equality of exponents. And it says if you got b to the p is equal to b to the q, then you can set p equal to q. Okay. What that means is we start with our large number and we try to rewrite it as the other number to a power. And 8 would be 2 to the third. Now equality of exponents says if these 2's match, then you can cross those 2's out and you set the exponents equal to each other. And once we set the exponents equal to each other in this problem, then we got our answer. Very simple idea, sometimes not so simple to get in the correct form. Let's take a look at this. 4 to the x is equal to 8. Well, if we start with our large number, the 8, there's no way I can rewrite 8 as 4 to a power. So this time I had to focus on both sides. And I notice that 4 is 2 squared, and 8 is 2 to the third. Now notice that the 4 to the x power already had a variable up in the exponent. So when we put our new exponent up there, we multiply them together, so 2 times x. Now equality of exponents, since they're both 2 to a power, you can cross the 2's out, and you set the exponents equal to each other. Oops. And solve them. So divide both sides by 2, and we get x equals 3/2. And that's our answer. Now let's consider this problem. If I try to use the equality of exponents, if I try to start with the larger number, which is 5, and try to rewrite as the other number to a power, there's no way. 3 to the first is 3, 3 squared is 9. There's nothing that I can raise 3 to a power to give me 5. At least integer-wise. Now we have a general definition for how to solve exponential equations. And our first step is to get the part with the variable and the exponent by itself on one side. Step 2, we're going to take a natural log of both sides. Step 3, use properties of logs to get the variable out of the exponent. Step 4 is solve for x. Okay, so step 1, get the part of the variable and the exponent by itself on one side. This is the part of the variable and the exponent. It's by itself. There's nothing in front of it. There's nothing after it. We simply have 3 to a power. Step 2, take natural log of both sides. So we'll have natural log of 3 to the x is equal to natural log of 5. Step 3, use properties of logs to get the variable out of the exponent. We have a variable up here. We can take that and put it out in front. That's from our properties of logs we saw earlier. Now we're trying to get x by itself, and natural log of 3 is just a number. So we're going to divide both sides by natural log of 3. Now when we do that, those natural log of 3's cancel. And we got x is equal to natural log of 5 over natural log of 3. Now if they wanted us to find the decimal approximation, I'd plug that in my calculator. Nothing exciting there. You push your ln button, 5, close parentheses, divide by ln 3, then close parentheses. Let me clear that off. And let's talk about log equations. So solving log equations. Step 1. Get everything with a log on one side, numbers on the other side. Step 2. Use properties of logs to get a single log. Step 3. Rewrite the problem in exponential form. This is the b to the p is equal to q definition. Step 4, we want to solve for x. And then step 5 is we want to check our answers. We want to make sure we don't end up with log of a negative number or log of 0. So if I had log base 3 of x minus 2 is equal to 1. Step 1. Get everything with a log on one side, numbers on the other side. Well, that's done. Everything with the logs over here, numbers over here. Step 2. Use properties of logs to get a single log. When all is said and done, you should just have log of something on this side, which we have. Step 3. Rewrite the problem in exponential form. The b to the p is equal q definition. Remember, whatever number is smaller that's set down here is your b, and whatever's right here is your q, and whatever's right here is your p. So our exponential form is b to the p is equal to q. Well, b was 3, p is 1, and q is x minus 2. And then we want to solve for x. That's step 4. So I'll take negative 2 over, it becomes a positive 2, and we get x is equal to 5. Although I won't work them completely, you may have some problems. We have multiple logs, like this right here. Now our first step is to get everything with a log on one side, numbers on the other side. That's done. Step 2 is to use properties of logs to get a single log. Here we have log of something minus log of something. And if you remember from the previous material, log of something minus log of something, subtraction becomes division. So this becomes log of x minus 1 over x minus 3 is equal to 2. Step 3, use your definition log to rewrite an exponent form. Remember, whatever number's right here is your base, and there is no number here, but it does say log, so that means our base is 10. Whatever's right here is going to be our q, and the other side will be our p. So we got b to the p is equal to q. So we plug in everything we identified. Well, b was 10, p was 2, and q is x minus 1 over x minus 3. And then you solve it down from there. I'm not going to continue that. Usually when I make these up, they don't come out where they actually work out or anything. One more topic I want to mention. If you have natural log of x plus 3 is equal to 7, a lot of students struggle with this because, well, what's a base? There is no base. That's correct. There's none listed here. But if you have ln, your base is e. So that's saying base is e. This will be q, and this will be p. Now it doesn't matter if it's natural log. All of our properties hold true. So our exponential form is b to the p is equal to q. B we said was e, p is 7, and q is x plus 3. Then I'll take the 3 over, and we get x is equal to e to the 7th minus 3. Now, I'm going to put YouTube videos out there that will present examples of these other topics. Solving exponential, or use exponential log equations in applications. This last topic that I want to mention is regression, mainly because I don't have a video on it. So that's why I want to give you an example. With your calculator, this is assuming you're given points. 2, 3, 4, 5. Let's say 1 is 0.1, 2 is 0.3, 3 is 0.9, 4 is 5, and 5 is 21. And we want to come up with a model for this. And I'm going to do it just for the exponential, but you could have a similar idea for the log. First thing we want to do is we want to put these in the calculator. So I'll go to my stat, do enter on edit, and if you have any numbers here, you just simply press your delete key and hold down. And it'll go through and delete them all. And over here, if I left arrow, press my delete key and hold down, delete them all. You definitely don't want to do that if you have L1 or L2 highlighted. It'll delete the list. Okay, so we got 1 through 5. So 1, 2, 3, 4, and 5. Now for L2, I'm going to have 0.1, 0.3, 0.9, 5, and 21. Now I want to exit out, so I'll do second mode. Now we need to go into our catalog. You don't have to do this but one time on your calculator. If we go into catalog by doing second 0, and then you push this button, looks like X and -1, that's actually your inverse button. That'll take you down to the D's. And we want to choose diagnostic on, which is right there, and then I'll press enter twice. Now if I do a stat, right arrow to calc, this is where your regression is. Linear regression is the line, quadratic is a U shape or upside down in, or not upside down in, and in. Cubic is that shape we talked about earlier. Quartic is like a W or an M. I don't know what that one is. We get down to here, and you see there's logistic, natural log, EXP. Let's choose EXP. Of course, this is natural log, and that's just our log. So if I choose EXP and then press enter, it comes back with a model. We got y is equal to a times b to the x power. So we plug in a and b. A, the 2 decimal places, was 0.02, and then times b, which 2 decimal places was 3.86, to the x power. And this would be our exponential function. Now the r squared in r tells us how good is our model. The closer it is to +1, the better for the r squared. Now the r can be a +1 or it could be a -1, but the closer it is to those, the better the model is. Now these are pretty close to 1, so that means it's a pretty good model. Now if I want to do the log, probably going to see something. Let's see though. Where's that? Stat, calc, and I want to choose I'll choose natural log. Press enter and then enter again. And that gives us a plus b. So we got a plus b, natural log of x. So we plug in our a, negative 3.9, rounded, and b is 9.77, and then natural log of x. Now you might look at that though and see that r squared and r are pretty far away from 1, so it's not a very good model. The reason why is because I designed it to be an exponential model. But anyway, that's how you do your regression on your calculator. Now I'm going to go ahead and stop the video here, and then I'll answer any questions you have.